A very fresh morning to all my dear friends and our very respected, very dear, very dear Rajkumar sir. Today I, Saurav, with all my project partner, is here going to represent our project topic and going to explain the working and principles of reciprocating pump. So starting with what is a reciprocating pump? So reciprocating pump is a positive displacement pump where certain volume of liquid is collected in enclosed volume, and it is discharged using a pressure to the required application. So reciprocating pump are more suitable for low volumes, and that also offer low flow with a high pressure. So in reciprocating pump, the cylinder is connected to the pump by a suction pipe, and it is connected directly to the delivery tank by a delivery pipe. Where at the cylinder ends, these pipes non-return valves are provided, and non-return valves allow liquid to pass in only one direction. Uh, Reciprocating pumps consist of a plunger or a piston that moves forward and backward inside a cylinder with the help of connecting rod, um, and also with a crank. The crank is rotated by an external source of power, which we deliver to it. Through the suction valve, liquid can only admit it to cylinder, and through the delivery valve, liquid can only discharge into delivery pipe. Uh, so now we'll move to the main components of reciprocating pump, as it has many important components in it, but we'll only talk about few specific parts of it. Few of the parts are described in this diagram, like suction pipe, suction valve, delivery pipe, delivery valve, cylinder, piston and piston rod, crank and connecting rod, strainer, air vessel. So starting with the suction pipe connects the source of liquid to the cylinder of a reciprocating pump. The liquid is sucked by the pipe from the source to the cylinder. So next here it is suction valve. Suction valve is a non-return valve, which means only one direction flow is possible. In this type of valve, this is placed between the suction pipe inlet and the cylinder. During suction of liquid, it is opened, and during discharge, it is closed. Talking about the delivery pipe connects cylinder of the pump to the outlet source. The liquid here is delivered by desired outlet location through this pipe. So next is delivery valve. Delivery valve also non-return valve placed between cylinder and delivery pipe outlet. It is in closed position during suction, and it is on the other hand it is open position during the discharging of the liquid. So cylinder is a hollow cylinder made of steel alloy, specifically of cast iron. Arrangement of piston and piston rod is inside the cylinder. Suction and release of liquid is like it takes place in in the both ways, so that the suction and delivery pipes along with valves are connected to the cylinder. Piston and piston rod. Piston is a solid type of cylinder part which moves backward and also forward inside the hollow cylinder to perform suction and deliverance of the liquid. Piston rod helps. It also helps in the piston to its linear motion. Crank and connecting rod. So crank is a solid circular disc which is connected to power source like motor or like engine, etc. for its rotation. Connecting rod also connects the crank to the piston. As a result of rotational motion of crank gets converted into linear motion of the piston. Um, so our next part is our next component is strainers. Strainers is provided at the end of the suction pipe. It is used to prevent the entrance of solid from water source into the cylinder, so that no other wastage or any debris cannot enter the cylinder. So our last working component here is air vessel. Air vessels are connected to both suction and delivery pipes to eliminate the frictional head and to give uniform discharge rate to the cylinder. My friend Saurav Kumar Jha will here explain the working of reciprocating pump. Over to Saurav.
So, as Saurav explained the basic introduction and various major components of the reciprocating pump, I will let you all go through the working and the classification of reciprocating pumps. So, for the working part, I am going to present my screen and show you the diagram. So basically, as Saurav explained, all the major components, which included the connecting rod, crank, piston rod, and the suction pipe, suction valve, and cylinder. So in reciprocating pump, when power is supplied to the pump, the pump power supplied makes the crank move, and by crank, the connecting rod is connected to the piston. The piston moves. So when the crank moves to the extreme rightwards, the piston comes to leftwards, and the suction is created here. So through the suction, the water is filled up in the pipe. Later on, when crank moves towards leftwards, the piston exerts force in the water towards leftwards, and the water delivery is done through the delivery pipe. So basically, this is about the working of the reciprocating pump. Now I will let you all through the classification of reciprocating pumps, like on what basis the reciprocating pumps are classified. So for the classification part, there are two types of classification that is done. That is based on the single acting or double acting. That basically involves the movement of piston, like when the crank and the piston move. So what is the movement on this? And other classification is based on the number of cylinders the pump is having, like single cylinder, double cylinder, or triple cylinder. So for the single acting reciprocating pump, as it is very clear by its name, like there is only one suction and one delivery. When the crank moves, the piston moves one times, and the suction and delivery is made simultaneously. Like there is no other pump and no other stroke for the delivery scheme or delivery function. But in the double acting reciprocating pump, the double acting reciprocating pump has two suction and two delivery pipes. So there are basically two delivery pipes and two suctions are done for delivering the water to power supply through the pump. Later on in the classification, we study about the single cylinder and double cylinder and triple cylinder pump. For the single cylinder pump, I will let you know through these diagrams, which will help more in the explanation. In this, there is double cylinder pump, as we have later on done the single cylinder pump. In single cylinder acting pump, there is only one cylinder present, and the piston movement is done in only one cylinder. But in double cylinder reciprocating pump, we have two cranks set at like in some uh, theta angle difference between them, and basically that theta angle defines the movement of the piston. So we have this as the rotation motion of the crank, produces the linear motion of piston. So this is basically acts like a phase difference between these two movements. So if the theta is set, let's say, set to be 180 degrees, so when the piston is at its extreme left position, the another piston is at its extreme right position. So this is basically double acting reciprocating pump, in which there is two cylinders present, and movement two pistons are moving in two cylinders to deliver the water supply. Next, we are going to cover this triple cylinder reciprocating pump. As we can see, this is a perfect ideal condition of triple cylinder reciprocating pump, in which three pumps are set at theta of 120 degree. Like the pumps cranks are at 120 degree of each other. So when one pump is at extreme right position, other is at extreme left position, and the third cylinder piston is at extreme right position. So basically, this makes the piston moves with a variance and with some phase difference between these two. And due to presence of three cylinders and three pistons, this type of pump is classified into triple cylinder reciprocating pump. Now my fellow partner Saurav Sinha will take over from there and let you know through the discharge and all other things. Saurav.
Okay, so now I'm going to explain the discharge through a reciprocating pump. So,
Saurav, do you
discharge is
wish
basically,
present? Do you wish if
yes,
I present anything?
okay, yes, wait,
Okay, I'm presenting this PPT. You can go through.
okay, you present.
Saurav, start.
Okay, so discharge is basically the volume flowing per second. So we need to calculate the volume which is flowing per second, volume of the liquid going out per second, multiplied by the number of revolutions per second. This is how we can calculate the discharge. So as we can see in the PPT that we assume A equal to area of cross section of cylinder and R equal to crank radius. Capital N is RPM of the crank and capital L is the stroke length, which is 2R. Now discharge. Now as we can see here, uh, discharge um, in case of the pump which is single acting, we can see that discharge through pump per second equal to area into stroke length into RPM divided by 60. So Q here equal comes out equal to A into L into capital N upon 60. This is the discharge when the pump is single acting. Now you can see discharge through reciprocating pump uh, in a double acting pump. So as you can see here, one more component adds up. So discharge comes out to be ALN upon 60 plus A minus AP into ln upon 60. Here AP is the area of cross section of piston rod. However, if area of the piston rod is neglected, then discharge per second equal to 2 ALN upon 60. So discharge per second equal to 2 ALN upon 60. Now the discharge of a double acting reciprocating pump is twice than that of a single acting pump. Now, owing to the leakage losses and time delay in the closing the valves, actual discharge QA usually lesser than the theoretical discharge, which is QTH. So now I'd like Stuti to take over and explain the next topics.
So moving on further to the slip portion, a slip of a reciprocating just a slip of a reciprocating pump is defined as the difference between the theoretical discharge and the actual discharge. Due to water leakage during pump operation, the actual discharge of reciprocating pump will be less than the theoretical discharge, as we can see in our equation. So slip is equals to QTH minus QA. So moving on further to the next expression, that is slip can also be expressed as a percentage. So we can say that percentage of slip is equals to QTH minus Q actual by QTH into 100, as we can see. So, moving on to the next part, the factors that affect the pump slip. There are three factors that affect the pump slip, that is differential pressure, fluid viscosity, and clearance dimensions. So, moving on to the next slide. So our next topic is what is negative slip. So negative slip So, negative slip occurs when the theoretical discharge is less than the actual discharge. Uh, so we can see in the previous slide. So we can see in this slide that when the QTH is less than Q actual, then the slip would be negative. Uh, so now the factors due to which the negative slip occurs, there are also three factors. First, due to high speed, due to short delivery pipe, and due to long suction pipe. So it mainly happens because of inertial pressure in suction pipe will be large as compared to pressure of the delivery valve. This causes delivery valve open during the suction stroke is completed and due to which our negative slip occurs. So now from here Suchit can take over.
So as the slip part has been explained by Stuti, so coming to the power of the single acting reciprocating pump that occurs. Now, first of all, briefing about the single acting reciprocating pump. What it is exactly is that in this there's only one side which is engaged to the fluid that is being displaced. A very simple example of this we can have is a syringe that we use in our hospital that has only one way to for the fluid to be displaced. So here, as you can see in this slide, that there is a HSSD. So what is this actually? This HS and SD. So HS is our suction head, and HD is our delivery head. So HS, that is suction head. This is a difference between the center line of cylinder and the pump, and our HD is our that is the difference between the center line of the cylinder and the outlet of the delivery pipe. So the power is actually the work done per unit time for this fluid to take from HS height to the HD to the delivery pipe. So that is the power that exactly occurs. For calculating this power, the expression that we use is that we use our flow rate of the fluid. We multiply the flow rate into the total developed head, that is our total static head, and the density of the fluid and the acceleration due to gravity that occurs of the fluid. So we can use over this slide that you can see the power input output that is to be expressed through the expression that has been as shown here. The flow rate multiplied by total discharge and the acceleration due to gravity and the static head. And the discharge one has been explained by my fellow partner Saurabh Sinha, and that is ALN by 60. That is for our single reciprocating pump. And this total static head, that is HS plus HD, which you can say total static head. And as we know that anything that occurs is not 100% efficient. So if there is a eta, that is the efficiency of our pump, so in that case we can calculate our actual power by this expression, that is 1 by eta, and our the expression for the power of the pump. Now let's have an example that till now we've understood the slip concept, the total theoretical discharge, and the power. So based upon that, let's have an example problem. So here we are given the single acting reciprocating pump where our discharge is 0.018 meter cube per second of water, and our running speed is 60 rpm, and the stroke length is 500 mm. So all we have to convert in the required measurement and unit, like millimeter into meter and all, and we'll calculate. And here we have as we have been given total lift, that is our total ln by 60 for single reciprocating pump. So we will calculate our theoretical discharge that will come out through this expression is 0.019 meter cube per second. And now coming to the slip part, that is our difference between theoretical discharge minus actual discharge. So actually our theoretical discharge is greater than our actual discharge. So will difference, and we will get difference the slip that is 0.001 meter cube per second. Now calculating the percentage slip, that is our difference between our theoretical discharge and actual discharge upon my theoretical discharge, that will come out to be 5.26%. Now it is actually a positive slip, that because theoretical discharge is greater than our actual discharge. Now coming to the coefficient of discharge, that is the ratio between the actual discharge and theoretical discharge. That will come out to be 0.947. Now coming to the theoretical power required input, that will calculate through our experiment that has been explained by me in the previous slide, that is rho now this theoretical discharge and acceleration due to gravity and the total static head. Now here we are neglecting the losses that I've explained, the eta, the efficiency. We are considering the negligible loss. So considering that, we'll have putting the values, we'll get our theoretical power input, that is 2.796 kilowatt. Okay. Now coming to the differences between the reciprocating pump and the centrifugal pump. So the basic difference between the reciprocating pump and the centrifugal pump is that in reciprocating pump there's a low flow rate and a high pressure up to about 700 atmosphere, while in our centrifugal pump there is a high flow rates at moderate pressure of a few atmosphere. Now, in reciprocating pumps, at constant speed, constant flow rate occurs at widely different outlet pressure, while in centrifugal pump, at constant speed, variable discharge occurs depending on outlet pressure. Now, in reciprocating pump, there's a low speed operation, while in centrifugal pump, there's a high speed operation. And here in reciprocating pump, there is high efficiency around 90% and remains constant over the entire operating range. While in centrifugal pump, the efficiency is around 80% and it varies in the operating range. So these were the basic differences between the reciprocating pump and the centrifugal pump. So now take over to the Sumit. He will explain the further parts. Thank you.
Thank you, Suchit. Now I'm sharing my screen. Wait. I hope my screen is visible and my voice is loud and clear. Uh, Now I'm going to give you a brief about various design consideration that will be taken.
Screen not visible. So
Uh,
now it's
hold
visible.
on.
Now it is visible.
Okay. So as I'm saying, now I'm going to give you a few design consideration that will be taken while designing or installation of a reciprocating pump. As my fellow admins have already told you about various design consideration in components and various fabrication, let me tell you about various design and fabrication that must be taken into account of the suction and discharge piping according to the best practices of the industry. It is important that the piping design and fabrication is done right the first time. Otherwise, it is very difficult to improve it in the future. The first consideration in the design of a piping system is the sizing of pipe. The capacity must be established not only for the entire system, but for the individual branches as well. The design flow should not be oversized by a large margin to prevent throttling of valves and wasting energy. The goal of selecting the pipe size of the system is to maximize the pipe size used while minimizing the cost of the pipe. As the pipe size increased, the system heads loss due to friction. Additional consideration must be made for pumping viscous material. Viscous material have a great friction loss than water in the same size pipe, as we have discussed in the class as well. The size of the suction and discharging pipe should be at least the size of a pump connection. Suction pipe should be one or two sizes larger than the pump connection and should never be smaller. A reducer can also be used in the suction line to allow for the suction pipe that is oversized. The overall design of the piping system should be as straight as short as possible with a minimal amount of bends or turns in the system. During fabrication, a simple method to determine if pipe flange faces are parallel to see if you can visibly see a difference in the flange face planes or not. Now, coming to the support, beside proper fabrication of a piping system, it is important to properly support the pipe as well. If no pipe support exists, the pipe strain will induce stresses into the equipment and support system. In determining the proper support of a piping system, the force and the moments of piping system must be calculated. The calculation must include the weights of the pipe, the liquid in the pipe, and the pipe insulation. Thermal expansion and contraction must also be taken into account. Because of various pipe strain, many effects could also be seen. They include couple misalignment, cracking of the piping nozzle or pump casing, distortion of pump casing and bearing housing, excessive vibration, leakage at the pump flange, and many more. Now, let me tell you about the various effect of acceleration on velocity and pressure in the suction and delivery pipe. First, let me discuss about the acceleration effect of acceleration at suction stroke. First, at the time of starting of a suction stroke, when the piston will start to move from inner dead center towards the outer dead center, liquid will have an acceleration and zero velocity at the inner dead center. Velocity of the liquid will be increasing, and therefore acceleration of the liquid will be decreasing at the beginning of suction stroke. Because of this acceleration, the suction head will be needed more as compared to the static lift. Liquid velocity and acceleration in the cylinder and in the suction pipeline will be related to their cross-sectional areas. As cross-sectional area of the pipeline will be less than the cross-sectional area of the cylinder, liquid velocity and acceleration in the pipeline will be more than the liquid velocity in the cylinder. Therefore, at the beginning of the suction stroke, when theta is equal to 0, pressure head inside the cylinder will be more than the static lift, and it will be equivalent to Hs plus Has, which will be lower than the atmospheric pressure head, as shown in the figure. Therefore, at the middle of the suction stroke, pressure head inside the cylinder will be equivalent to the static lift, which will be lower than the atmospheric pressure. Further, velocity will be decreasing from its maximum value at the middle of the suction stroke and will become 0 to the end of the suction stroke. Now, let me tell you about the effect of acceleration of piston on velocity and pressure in delivery pipes. Similarly, at the beginning of delivery stroke, pressure head inside the cylinder will be more than delivery head, and it will be equivalent to delivery head plus Hd plus Had, which will be above the atmospheric pressure, as shown. Velocity of the liquid will be increasing and acceleration of the liquid will be decreasing at the beginning of the delivery stroke. Again, at the middle of the delivery stroke, velocity will again become maximum, and then at the end, acceleration will become 0. Therefore, at the middle of the delivery stroke, pressure head inside the cylinder will be equivalent to Hd, which is a delivery head, and which is above the atmospheric pressure head. Furthermore, velocity will be decreasing from its maximum value at the middle of the delivery stroke, and it will become to 0 at the end of the delivery stroke. Therefore, at the end of the delivery stroke, pressure head inside the cylinder will be equivalent to Hd minus Had, which is above the atmospheric pressure. Now, let me give you about the effect of friction in suction and delivery pipe. Using the Darcy equation that we studied in class, we can calculate the friction loss due to friction loss, head of friction loss in suction pipe and delivery pipe, as shown in front. So, at the beginning of stroke, when the theta is equal to 0, sin theta will equal to 0, and head loss due to friction will be 0. And the middle of stroke, when theta is equal to 90 degree, sin theta becomes 1, and the head loss due to friction will be maximum. Again, at the end of the stroke, when theta is equal to 180 degree, sin theta will become 0, and head loss due to friction again comes back to 0. So you can see that there is the frictional head follows a parabolic curve, which is parabolic in nature. We can also calculate average frictional loss in the pipe, which is equal to 2 by 3 of HFM. Now, my partner Suraj Mato will continue from here.
Thank you, Sumit. So over here, students, can you present the screen, please? So over here, I will talk in short that how reciprocating pump works. Then I will tell that what is the purpose of an air vessel in a reciprocating pump. Okay, so this is a single acting reciprocating pump. So when the crank spins, the rotatory motion gets converted into reciprocating motion, due to which the piston rotates between IDC and outer dead center. Suppose piston is moving from IDC to ODC, so what will happen? The inner pressure of the cylinder decreases. Due to that, the inlet valve automatically opens, and then water will fill inside the cylinder. So now in this case, the piston starts traveling towards IDC. So what will happen? The pressure starts increasing in cylinder, due to which the inlet valve will automatically close, and outer valve will automatically open, and the water pumps out through delivery pipe. So what is the problem over here is that the water flow is not continuous, because in one half of the cycle it is pulling the water, and the other half it is delivering the water. So in case we want continuous flow of water, we do not want this discrete or intermittent flow water, then we can use the air vessels. Basically, air vessel is a dome-shaped vessels which is connected at the delivery and suction pipe, as you can see in the screen. So inside the air vessel, we can see that up to some level there is a water, and over there there is some air is present in the vessel. So moving on. Now what happens? Previous slide. Now what happens? Suppose the piston is moving from IDC to ODC. So it's pulling water inside the suction pipe. So when it is moving towards the inner dead center, piston pushes the water to go out. Then this suction valve will close and delivery valve will open. Actually, what happens? The water moving out of the cylinder is at a very high pressure. So some amount of water will comes out of the delivery pipe, but due to high pressure, some amounts of water will enter inside the air vessel and compress the air. In next half of the cycle, the piston again start moving towards the outer dead center, and that time it is busy in pulling the water inside the cylinder. But the air inside the air vessel is in a high pressure. So in that case, the air pressure will do its job and it will force the water to come out of the delivery pipe. So what we have seen that water flow in this case is continuous. First time piston is forcing the water to come out of the delivery pipe, and the second time the air pressure is forcing the water to come out of the delivery pipe. So let's talk about the what are the advantages of air vessels. So first of all, it makes the flow almost continuous, and the second advantage is that by fitting air vessel as close as to the pump, the length of the pipe in which acceleration head occurs get reduced. This reduced acceleration heads and the pump can be run at the much higher speed without any risk of separation. Moving to next slide. So here, by fitting air vessels, we can reduce the friction head losses and in the suction pipes and delivery pipe. So we can save some amount of energy. तो ये जो एनर्जी सेव हो रही है उसमें हम कैलकुलेट कर सकते हैं वर्क डन निकाल के। जो डिफरेंट सिनेरियोज हैं, एक तो जब हमने एयर वेसल यूज करा और एक दूसरा केस जिसमें हमने एयर वेसल यूज नहीं करा. So in दोनों के difference we can easily calculate that how much energy is saved. Moving to next slide, and these are the equation that you can refer to calculate the suction head and the head loss and friction loss in suction pipe and the delivery pipe. Moving to next slide. So here we can see that how work done is calculated in suction stroke and the delivering stroke. Moving to next slide, please. So around 85% of the work हम save कर सकते हैं by using the air vessel. So from now on, my batch partner Shriyans will continue from here.
So, hello everyone, my name is Suryash Shingwar and I will be speaking on the last topic of our presentation, which is the indicator diagram. So, the indicator diagram is drawn between the pressure inside the cylinder versus the current crank angle. From what we have seen in the working, whenever the piston moves from inner dead center to outer dead center, it needs to apply some pressure so as to pull in the water and then deliver it to the destination. So we have represented it in the further diagram, which is the ideal indicator diagram. Here, the crank moves from angle 0 to 180, then back to 180 to complete a full revolution, and follows the path of J, K, L, and M. So from J to K, the crank moves from inner dead center to outer dead center, and thus needs to apply pressure more than the current suction head, which is we have represented here as H is below the current atmospheric pressure, which from where we actually take the water. Now, from here the crank moves from again from outer dead center to inner dead center, and thus again needs to apply pressure higher than the current delivery head so as to deliver the water at the destination. This diagram is, however, completely theoretical because we have left out three major components which greatly affect this diagram, which is the changes due to acceleration head, changes due to friction head, and changes due to velocity head. So now here we have administered the change in the diagram due to acceleration head, which we can see has made the diagram a little skewed. This is because of the inertia of water. When the initial section is undergoing, the water is at zero velocity and is therefore required to be at certain velocity to enter the cylinder. So from to put the water at this velocity from zero, we need to apply some acceleration and thus some extra energy. This extra energy is compensated in form of acceleration head, which here is represented by J and P, and similarly occurs on all the 4 points, therefore skewing the indicator diagram. Moving on, the next effect is effect of friction head. So friction head in any pipe system is directly proportional to square of velocity. since the square velocity is also since the velocity is also proportional to current crank angle, we can obtain a parabolic curve of the friction head versus the current crank angle, which is depicted here from line P, E, and Q. So this is further change the indicator diagram. Now the third and the last change is occurred due to the velocity head, which is represented here by Vs square by 2g. This Vs is nothing but velocity of water in the section head, whereas here it is represented by V square d by 2g, which is velocity in the delivery head. These values are different because the area of pipe can be different as per a requirement. So this is the complete and the practical indicator diagram of a real reciprocating pump. So the purpose of this diagram is to actually calculate the work done by the pump in one stroke length. Thank you. And this is a complete formula which we can derive.
Okay, so topic completed.
Yes.
Okay, recording one. Okay. Thank you all. Thank you everyone.